Okay guys, so today we're going to be looking at wave-particle duality. This is the final part of the AS quantum chapter. Now, last time we looked at the photoelectric effect, and this kind of built on our idea that light can behave as a particle. We've seen already that light can behave as a wave. We've done that for ages. Anything with diffraction, Young's double slit, we've seen that. You've been seeing that since GCSE. Recently, we've looked at the idea that light can behave as a particle. The gold leaf electroscope that we discussed last time, and how that is explained by the photoelectric effect. There's evidence for light as a particle. Today's something a little bit different. Today, rather than looking at light, we are going to be looking at particles, and particularly the electron we're going to use most of our examples with, but everything that we actually talk about today holds for all particles really. Scientists have done experiments with much larger particles than electrons. When I learned this, they used carbon-60 buckyballs, I think they're called, but they may well have shown this with particles bigger than that since then, I'm not sure. But we're going to do most of our examples with the electron. Now, we have always seen the electron behave as a particle, okay? We know it has mass, it has charge. The photoelectric effect is evidence of the electron being as a particle. Pretty much everything we've done in physics, everything you would have done through GCSE, you would have always considered an electron to be a particle, okay? It has some mass, it has a certain amount of charge. But what we're going to do today is we are going to say, hang on a minute, can these things that we always consider to be particles, can they behave as waves? Okay, and what I'm going to show you first is an experiment basically that, well, I'm not physically going to do the experiment, but I'm going to show you on the board an experiment that has shown us evidence, clear evidence that electrons do in fact behave as a wave rather than as a particle in certain circumstances. Okay. Okay, so I'm going to talk you through what we've got going on here. Now, the first section of this, you will hopefully recognise. All of this here, you will recognise as an electron gun, okay? You would have seen that in the past. To talk you very, very quickly through it, we've basically got a heated wire here, a hot wire. It's going to be emitting electrons by thermionic emission. These electrons are then going to be accelerated across quite a high potential, well, usually quite a high potential difference. Towards this positive plate here. So they're going to fire through this gap, and we're going to have basically electrons firing out here, okay? You can control the speed or the energy that these electrons leave by changing the voltage of this potential difference here. And we're going to be talking about that voltage, reminding us about how that links to the speed of the electrons when we do some of the worked examples later on. Now, what goes on here is more important though. Now, this here is basically, it is a crystal of particles that are quite evenly spaced, or nice and aligned quite evenly, basically. Okay. In the book, they use polycrystalline graphite. I'm not an expert on what that is, but it's basically you've got quite evenly arranged particles. Okay. It can work with other things as well. Now, the important thing here then is this. Okay. When these electrons go through here, what we then observe, the other side, when we've detected these electrons on a screen basically, okay, what we observe here is we observe an interference pattern. Now I've drawn this as a circle here because it will interfere in all directions going through here. It's not just like a little slit or a double slit in the Young's double slit experiment where you'll get an interference pattern in one plane. In here, it's going, you've got your light coming through and it's going to go spread out like that, and it's going to spread out like this, okay? So you get an interference pattern. You've got your first or your central maxima effectively, and then you've got a first, a second, and a third maxima coming away from that. Okay? Let's put that on silence. So we've got our interference pattern here, and we know that an interference pattern is evidence that diffraction has happened, okay? And this is the fundamental thing here. This is the ultimate evidence that these electrons traveling through here, they're not just traveling as particles, but they're actually traveling as waves, okay? If you send one electron through here, okay, if you send a beam of electrons through here, sorry, you are going to get some of them going straight through and some of them getting diffracted and all over here, and you're going to get this interference pattern. Evidence of a wave. We know that from our waves chapter. A little bit of the detail going on here. So in order to get this to work quite well, we know that for diffraction to happen, we need the wavelength of a wave to be similar in magnitude, in size, to the size of the thing that's causing it to diffract, basically, okay? So for example, if you had a sound wave with a wavelength of 1 meter, it would diffract quite well going through a door, which is 1 meter wide, okay? If you have a light wave with a wavelength of 500 nanometers, it's not going to diffract very much as it goes through a door that is 1 meter wide. So what we need to do here, because the separation of the atoms in these materials, separation of atoms is something on the scale of around 10 to the minus 10 meters. What we're looking for is these electrons to be traveling along here with a wavelength. I know it sounds weird, electrons, wavelength, strange, but we're looking for these electrons to be traveling along with a wavelength of around about 10 to the minus 10 meters. Okay, so how do we calculate this? How do we know what the wavelength of an electron is, or a beam of electrons? It's a strange thing. Fortunately for us, there is an equation, okay, and it is it came up by a scientist by the name of de Broglie, spelled de Broglie, okay, whose name was de Broglie, as far as I'm aware anyway, okay, and the equation that he came up with, he basically said that the wavelength is proportional to 1 over the momentum of the electrons, okay? So I'm going to write this as MV just to make it clear. So, okay, so the wavelength is proportional to 1 over the momentum, and it turns out that we can actually put this into an equal sign with our constant of proportionality, and it's no surprise here in the quantum chapter that our constant of proportionality is in fact Planck's constant. So we end up with an equation that says this: the wavelength is equal to h over mv. Okay, and this is a really important equation. Now this is the one that we're going to be focusing on in today's lesson, but just a little bit of an exam tip here. Okay, when you're kind of stressing in your exam and you're looking at your equation sheet in the exam, if you don't know all the equations, you may know them by then, but you've got the equation sheet. You're looking at your equation sheet and you're thinking, which is the equation for the photons and which one's the equation for the electrons? Well, the following equations are going to be there. You've got this one. You've also got E equals hf and E equals hc over lambda. Okay, and you will have seen these so many times, and you probably won't have this issue. But sometimes you'll be stressing in the exam, and you think, oh my god, which one do I use? Well, the one that is for particles, i.e. electrons, okay, things that have mass, is the one that's got mass in the equation, okay? The ones that do not have mass, these don't have mass, there's no m anywhere in those equations. The ones that do not have mass, they are for photons, okay? They are for light. And that's just a very quick exam, sort of exam skill really, exam tip, just to help you if you have that moment where you're not sure which equations to use, okay? I'm going to forget about those now, I'm going to stick with this. Okay, so this is our equation. Okay. Now we can actually use this to investigate what is going on inside materials. Okay, so if you know the information about your electron, so you know the speed that it's traveling at, okay, you know the mass of the electron, which we do know the mass of an electron, the rest mass of an electron, okay, you can work out what its wavelength is. Okay, and then what you can also do is you can then use this diffraction pattern here to work out what is going on inside here, okay? Now, I'm going to give us a little bit of a cross-link to another part of the course, okay? It's a part of the course that kind of comes into the waves chapter a little bit, but the exam board that we've been using, they tend to put it into the stars section, into the sort of analysing starlight, but basically it's a waves equation, and it should be, in my opinion, with the diffraction stuff. So what we can actually do is we can use the following equation, which hopefully you have seen up to by this point, which is that n lambda equals d sine theta. And this is for, we use this for waves, usually for light, but we use this for waves when you've got a wave and it goes through a diffraction grating, okay? There's a spectacular diagram of a diffraction grating there, okay? And then you will always have a central maxima, and then you will have some more maxima angles here, okay? So you would then have your first order maxima, you might have a second, third, fourth maxima, okay? Where this angle here is theta. So just like when we have light going through a diffraction grating, I'll just clarify all my terms, by the way. So D here, I can never remember if it's a capital D or lowercase, it doesn't really matter. Okay, so D here is the slit separation, okay? N is your order of maxima here. Theta is obviously your angle here, and lambda is obviously the wavelength. So what we can do is, if we actually fire these electrons through here, okay, if you know the wavelength, you can measure the angle, okay? You can measure the angle to the first or second or third order, you just change your value of n. You can measure the angle here, and then you can actually work out what the slit separation, which in the sense here is going to be your atomic spacing in the crystal, okay? So you can actually work out what's going on inside that material. You can do this with an electron beam here. You can do it with X-rays, okay? X-rays, because they have a wavelength of around about 10 to the minus 10 meters. Now again, I am by no means an expert in the field. My belief, my understanding, I think, without checking it, is that the advantage of doing this with electrons, with an electron beam instead of an X-ray beam, is that it's not that easy to get a beam of it's not that easy to get an X-ray pulse or an X-ray beam at a very specific wavelength, okay? Usually when an X-ray is created, you're going to have it's something we do in year 13, but you have what we call a Bremsstrahlung X-rays, where they have a vast range of energies, and you get characteristic X-rays which have more specific, but ultimately it's quite difficult to create a beam of X-rays that have only one specific wavelength, like a laser, like a monochromatic light, for example. Whereas with these electrons, we can do it much more easily, because we know exactly what voltage we have here, exactly what energy the electrons are being fired out, okay? The only difference really will be if an electron in a thermionic emission, it might be emitted in this direction with a bit of kinetic energy already. Maybe it was in this direction with a bit of kinetic energy, but that's going to be negligible, okay? So, just to clarify those points, we can use X-rays or an electron beam acting as a wave. We aim it at this crystal of material here. Polycrystalline graphite is what they use in a book. And we get some diffraction, because the atomic spacing here is similar to the wavelength of our electrons. And then we get an interference pattern over here. And with our interference pattern, we can use this equation, which you may have seen, but you may be introduced to it in year 13 in the stars section. And we can actually work out what the spacing is here, okay? Interestingly, there are some kind of approximations of ways of modelling this experiment. I did this experiment in my first year of university, and instead of using X-rays or electron beams and a crystal here, we used, if my memory serves me right, it was 12 years ago, we used microwaves, and the department had created like a big polystyrene block with some metal ball bearings separated a few centimeters apart, and we basically had to inside this big white polystyrene block, we couldn't see where the metal ball bearings were, and we had to basically fire microwaves through, and with microwave detectors we would work out where the maxima were, first order, second order, and we could then use this equation to work out what the spacing was between the metal balls. Okay, it was a really interesting approximation to this experiment, basically on a bigger scale. Okay, we can theoretically use this equation to work out the wavelength of any physical object, any particle of such that is moving along. Okay, but I'm going to do, before I go on to the worked example questions I want you to have a go at, or that I suggest you have a go at, I'm going to show you how this becomes unrealistic in essence when we are using things that aren't on like an electron or an atomic scale. Okay, so let's say, for example, a person. Let's say you've got an Olympic sprinter, someone like a Usain Bolt, okay, and they are running along. Let's see, what is the wavelength of Usain Bolt as he is running down the track? Okay, now Usain Bolt has a mass, I don't know what Usain Bolt's mass is, probably about 85 kilograms something, so we're going to say Usain Bolt has a mass of 80 kilograms. Let's make it 100 to simplify the maths. Okay, so 100 kilograms. He is running at a speed of, well, he probably reaches a high speed, but on average, as he goes down, 10 meters per second. Okay, so our momentum is 1,000 on the bottom. Okay, we know Planck's constant is 6.63 times by 10 to the minus 34. Okay, so what we're saying here is that our wavelength is 6.63 times 10 to the minus 34, let's call it 7 times 10 to the minus 34, divided by 1,000. So we're saying our wavelength here for Usain Bolt is going to be 7 times by 10 to the minus 37 meters. Okay, now 7 times by 10 to the minus 37 meters is so small that it isn't going to exist. It can't exist. It just isn't anything. There's nothing we can't do anything with that. It's a meaningless number. Okay, so objects of a day-to-day size, a macroscopic size, whilst technically we can still use this equation for them, it's going to be complete nonsense. Okay, it's only really going to work for things on a much smaller scale. Okay, and looking at it the other way, okay, what we can do is we can actually use this idea here to explain a few things. Firstly, we can use it to explain why humans have a lower limit to the size of things that they can see. Okay, so even if you built the best microscope in the world and you did all kinds of things with it, like, there's only so small you can physically see with visible light. You cannot see atoms with visible light. Any equipment that we use to physically look at atoms, it would be like a scanning tunneling microscope or an electron microscope or something, where they're using different techniques and they're recreating an image of an atom, but we can't actually see things with visible light on an atomic scale. And the reason for that is because if we think about it, we know that the atomic spacing here is about 10 to the minus 10 meters. So atoms, we're looking at around about 10 to the minus 10 meters. Now we know that visible light is 10 to the minus 7 meters, there or thereabouts, about 1,000 times bigger than the atomic spacing. Okay, and therefore visible light doesn't interact with atoms in a way that's going to allow us to see individual atoms. Okay, because you are not going to get any kind of diffraction or anything. Like, the visible light is just too big. The wavelength is too big to interact with something on that smaller scale. Okay, we can also use this to explain why things like the Large Hadron Collider use very high energy beams, okay? They need to have particles that are traveling extremely, extremely fast, okay? Now, again, I'm not an absolute expert on these kind of things, but basically, if you want to look at something, just like I've said, visible light cannot look at an atom because the wavelength is too big. You would need to use X-rays that have a wavelength of 10 to the minus 10 in order to look at things that are this small. If you wanted to look at things on a nuclear scale, 10 to the minus 15 meters, you're going to need to use something that's got a wavelength of 10 to the minus 15 meters, or a particle beam that has a wavelength of 10 to the minus 15 meters. And if you want to look even smaller than that, you're going to need to use something that's got a wavelength even smaller than that. So when we're firing these particles, these hadrons, like protons and neutrons and things, when we're firing them around and colliding with them with each other in the Large Hadron Collider, we need to know that they are, in order to be able to interact on a really, really small scale, they need to have a very small wavelength. And to have a very small wavelength, with this being constant, we need to have a very, we need this number here to be larger, basically. So we need the momentum of these things to be higher. So the higher the energy of the particle, the faster it is, the higher the momentum the particle has, the smaller the wavelength is going to be, the smaller the thing you can investigate, okay? If we look at an example, okay, let's just say, for example, what would be the wavelength, okay? What would be the wavelength if we have, I think the Large Hadron Collider is working at several tera electron volts. So let's just say something like 8 TeV, okay? And what we'll do, I'm just going to clear this up a little bit, and we'll look at what kind of wavelength would a proton traveling with an energy of 8 TeV. I don't know if it is protons that they travel like that or what, but we'll have a look at this. We'll do some calculations, and I also need to remember what the mass of a proton is, okay? So 8 tera electron volts, let's convert that into joules. Now, let's say, so this is the kinetic energy. So kinetic energy equals half mass times speed squared. So we can work out what the speed is. We'll do it just step by step. So we'll work out what the speed is here, and then we can work out what the momentum is, and we can work out what the wavelength is. Okay, we could probably rearrange it and do it all in one step, but I'm going to do it step by step for us. So I'm going to divide this by 0.5 times by the mass, 1.7 times by 10 to the minus 27. It's actually 1.67 or something, but I'm rounding it. And then we're going to square root it, and that's going to give us the speed. Okay, and then we can then times this by the mass, which is again 1.7 times by 10 to the minus 27, and we are going to do H over all of that, so 6.63 times 10 to minus 34 over all of that. I'm going to get a proper calculator to do it. Yeah, so that gives us about 1 times 10 to the minus 17, okay? So equals 1 times by 10 to the minus 17. Now this is a very basic approximation, and the physics is probably fudged a little bit, but it gives you an idea, okay? An 8 tera electron volt beam of protons is traveling at such a speed, and again, I didn't even work out what the sorry, that's not speed. That is wavelength. Sorry. So let's try that again. So this gives us a wavelength of 1 times 10 to the minus 17 meters. Now, this as I said, the physics is fudged a little bit in the fact that I didn't work out the speed first, and so I don't know what kind of relativistic effects are going on, which there probably would be. There's other things, like I said, I don't even know if they do send protons at this energy or what, but it's a ballpark kind of idea. This might be out by a couple of factors of 10 or something, but this is slightly smaller than a nucleus, and we know that at the Large Hadron Collider, they're working out, they're investigating things that are on a nucleus and smaller than a nucleus scale. So that kind of makes sense. A very high energy beam, okay, was able to give us a high momentum for these particles, which meant we could get a small wavelength. And that means the wavelength interacting, okay, with things on its size, okay? Now it's not, like I say, it's not truly the same idea as what they're doing at the LHC in terms of they're not doing a de Broglie wavelength calculation. They're not doing a n lambda equals d sine theta. They're not doing interference like that. But things the energy has to work out, okay? Things with a certain amount of energy, a certain wavelength, are going to be able to investigate things of that size. That's a very simplified version of it, okay? Now, that was a bit of a sidetrack, but it gives you some context to what we're talking about here. What I'm going to do now is I'm going to go through some more straightforward worked examples that are a little bit more linked to what you're going to do what you're going to get in your exams, okay? What we're going to do is we're going to do calculations where you are given a voltage here, okay? You're going to have to work out based on this voltage, you will be able to work out what the wavelength of the electron is. So the voltage, you'd be able to work out the energy, you'd be able to work out the speed, you'd be able to work out the wavelength, and then you can make a decision as to whether or not you think you would get a good interference pattern here. We're also going to do the same in reverse. So we're going to say, we'll say something like what voltage would be needed to create an interference pattern, or what voltage would be needed to create a wavelength of a certain amount, something like that, okay? Okay, so these two questions, I'll read them out, and again, if you want to pause here and work them out yourself, I suggest you have a go at that. I will work through the answers following. So, first of all, would a potential difference, and that's here, okay, would a potential difference of 300 volts give a good diffraction pattern over here, okay? So would a potential difference of 300 volts give a good diffraction pattern? Okay, that's question A. Question B, what potential difference would give a wavelength of 1.5 times by 10 to the 10 meters? Simple as that. Okay, so I'll give you a little bit of advice. I mean, I'll pause. If you want to pause it here and have a go just on that, do so. I'll give some hints. You can then pause it and have a go, and then I'm going to work it all out. So feel free to pause it now. The hints are basically, if you're doing this, what you're going to do is you're going to take your 300 volts, okay? You're going to use that to work out how fast the electron is traveling. Now the step-by-step is that you're going to work out what is the work done on the electron, voltage times by charge. What is the work done on the electron as it accelerates across here. And then once you know that is the kinetic energy, use that to work out the speed of the electron. Then you're going to work out what the wavelength is, and if that wavelength is something on the scale of about 10 to the minus 10 meters, then you're going to get a good diffraction pattern. Bit either side's okay, but if it's miles away, 1,000 times bigger, 1,000 times smaller, it's not going to work, okay? I kind of just made this question up. I'm hoping it's either really good or really bad, but we'll see. Then this one, what potential difference will give a wavelength of this? We're just going to work backwards. You're going to say if the wavelength is that, what will be the momentum using the de Broglie equation? So if the wavelength, what would be the momentum? We know the mass of an electron, so you can work out the speed. With the speed, you can work out the kinetic energy, and with the kinetic energy, you can work out the voltage. Okay, I'm going to work those through now. So I'm I'll do this one first. Okay, question A. So, potential difference of 300 volts. So, the potential difference of 300 volts here. With an electron gun, our standard electron gun equation is EV equals half mv squared. Okay, so we can work out this. Now we know E is 1.6 times 10 to the minus 19, V is 300. We can work out half mv squared. Now let's just do a little bit of algebra here. So I'm going to say, EV. I'm going to say 2EV over m. I'm going to square root that. Is going to give me V. Now, it's something that's quite important here. I haven't mentioned up until this point, is that it's probably quite important to make sure that it's obvious which V we're talking about here. We've got volts, potential difference, voltage, and we've got speed. So you make your voltage V way bigger than it needs to be, and your speed V probably quite small, just to make it obvious here. So the square root of 2 lots of E of the electron charge times by 300 volts divided by the mass of an electron is going to give us the speed. We then know that the wavelength equals h over v. Okay, so I'm going to do this all in one calculation. So my wavelength is going to be 6.63 times 10 to the minus 34 over the mass of an electron, which is 9.11 times 10 to the minus 31, times by whatever that comes out as. Okay, so let's put that into our calculator. I'll write, and in fact I'll write it out here. So 6 about 7. We get a wavelength here of 7.1 times by 10 to the minus 11, which is quite annoying really, because it's kind of close. In fact, it's not annoying really, it's close. Yeah, it is quite close actually. So, you know, that's pretty close to being 10 to the minus 10. It's a little bit smaller, but it's pretty close to being 10 to the minus 10. So I would, with that one, I would absolutely be saying, yes, I would get a good diffraction pattern, because 7.11 times 10 to the minus 11 is fairly close to 10 to the minus 10. In exams, it's a sort of question where, to be honest, if they gave you an answer like that, you'd probably be able to give either answer. You'd probably be able to say yes and justify it, or no and justify it. And they don't really care. They just want to know that you understand. But here, I'm pretty sure I'd be saying yes, that would give me a nice diffraction pattern in this case. So let's look at part B. What potential difference would give a wavelength of 1.5 times 10 to the minus 10 meters? Okay, now just thinking about this first, this is a larger size, it's a larger wavelength than the answer we got for part A. Now for a larger wavelength, we're going to want a smaller momentum, and with a smaller momentum, you are obviously going to have a smaller energy. So I'm assuming this is going to give me an answer that is going to be less than 300 volts. So I would expect it to be somewhere between, you know, probably a couple of hundred volts maybe, but certainly less than 300 volts. So let's see what happens. Now, so wavelength. So lambda equals h over mv. So if we rearrange this, we can say that, bring the m up, h down. So I'm going to say m lambda over h is going to be 1 over v. I don't know why I did it that way. We'll flip them. So v is going to equal h over m lambda. Should have done it a bit easier than that. So v equals h over m lambda. Now, this is the speed, remember. So we know what the wavelength is, we know what the mass of an electron is, we know what Planck's constant is. I'm not going to write it all out on the board, every single thing here. I'm just going to type it straight in. So I'm going to go 6.63 times 10 to the minus 34, 9.11 times 10 to the minus 31, and 1.5 times 10 to the minus 10. See that? Yeah, okay, equals 4,851,811.196. 4851811. Fine. Right, so now what we're going to do, so now we know the speed, we can work out the energy, the kinetic energy. So I'm going to say, yeah, we can see there. So I'm going to say half times by the mass of an electron, 9.11 times 10 to the minus 31, times by the speed squared is going to give me the kinetic energy. Okay, so we'll do that step. So we're going to square that answer. 0.7 times 10 to the minus 17. That is in joules, okay, remember? So finally, we know what the kinetic energy now is. So we know that this electron here came along with a kinetic energy of 1.07 times 10 to the minus 17 joules. Okay, so we can now work out what voltage will be needed there. We know that the this is the kinetic energy, so it's the work done. So we're going to say that is equal to EV. Okay, you see that down there? Yeah. So I'm going to divide this by the electron charge to work out what the voltage is, and that's it done. Okay, so divide by 1.6 times 10 to the minus 19. It's going to equal 67 volts. So I was a bit high with my hundreds, but 67.0156 or something volts. Okay, so it's less than 300, which was the most important thing I predicted. Okay, so 67 volts is going to give me this energy here. Okay, that's about it really. Okay, on this chapter, there's not too much to it. Okay, the most important thing is understanding that particles. Okay, so in particular, we usually look at electrons, but particles, physical objects, can behave as waves. We can, if I just summarize. So physical particles can behave as waves, okay? We can work out what the wavelength of them is using this equation, lambda equals h over mv, okay? In the equation sheet, it might appear as h over p is like a momentum. But yeah, we can work out the wavelength of them using this, okay? We know that the electron gun equations are going to be very relevant, which is this one, EV equals half mv squared, okay? And also, as kind of an aside, it's certainly a good chance that it will come up in a synoptic paper, in a unifying concepts paper. This would link to our n lambda equals d sine theta equation for interference. Okay, so it's certainly something we could look at there. That's about it really. Okay, so thank you very much, and see you next time.